Now I will make the calculations for exterior long beam. Okay, here is a trapezoidal loading. Okay, exterior long beam. Okay, here is a exterior long beam. First of all, see these calculations. So total length was ly. Okay, so if this is lx, then the half will be lx by 2 due to 45-degree angle. Okay, if this is lx by 2, then this dimension will be lx by 2 due to 45-degree angle. Okay, lx by 2, and on the other side again this is lx by 2. Okay, because if this length is lx, then the half length will be lx by 2, and due to the 45-degree angle triangle, this length will be lx by 2. So the remaining length will be ly minus lx, means lx by 2 from this side, lx by 2 from this side. Okay, now first of all, this rectangular shaded area region area, here is ly minus lx. Okay, this is the length side and the width is lx by 2. Here you can see this portion area lx by 2. Okay, this dimension, okay, that is the half of lx. So lx by 2 multiply ly minus lx. Okay, plus there are two triangular portion. First of all, this triangular portion area is half into lx by 2 into lx by 2, means lx square by 4 multiplied by half. So for two sides, when multiplied with 2, so it will become lx square by 4. So here you can see lx square by 4 or lx square over 2 square. The answer will be same. So by simplification I will get, okay, you can try, that is the simplified form. Lx will be in multiply will inside. Similarly I will open this option, lx square by 4. Okay, here is lx square by 2, lx square by 4. Okay, this is means when you will simplify, the answer will become 1 by 4, because half is bigger than 1 by 4. So half will if we half, if we subtract again half from the half, then will become 1 by 4th. Okay, you can just use your calculator, that is simplified. Okay, then I have just common 1 by 2 lx into ly minus lx square by 2. Okay, that is the trapezoidal loading. Now I will convert this trapezoidal loading into equivalent UDL. Okay, again I will multiply the factor. Okay, what is the factor? Factor is f is equal to 1 minus r square by 3 divided by 1 minus r by 2. What is r? R is shorter dimension to longer dimension ratio. What is f? Factor converts trapezoidal load into equivalent UDL load for maximum bending moment at center of the simply supported beam. Means after conversion for the trapezoidal load to UDL load, we get the same maximum moment as we get from the trapezoidal load. Why we are doing? For the simplification of calculations. Okay, and if there is a scale panel, okay, you can put the value 1, the f value will become 4 by 3, the same value we have used in the interior short beam. Okay, now f is the factor. Now this is the trapezoidal load. Now I will multiply with the f to convert into UDL load. Here trapezoidal load, okay, multiplied with factor f to get the equivalent UDL load. Okay, so equivalent UDL load, first of all I will calculate what will be the equivalent width. For the calculation of equivalent width, you will multiply with this, divide with this dimension. For example, if you have the area of this, okay, you will divide with this length, you will get this equivalent width. Okay, so here is the, first of all, that is the formula of the trapezoidal load. Okay, multiply with f, that is a factor. Okay, and then divide by ly to get the equivalent width. Okay, so here 1 by 2 Lx into Ly, so I will divide with Ly. Okay, so just take common Lx from outside in this portion, Lx by 2, and divide with Ly. Ly, our Ly will be cancelled out, and here one Lx will remain and Lx by Ly will come, and Lx over Ly is equal to R. Okay, so here 1 minus R over 2, here is already 1 minus R by 2, this will be cancelled out, the remaining answer will be 1 minus R square by 3. Okay, and if in the exterior side, other side, if any cantilever portion, you will add the cantilever width, otherwise this is the equivalent for the exterior long beam. Okay, for the interior long beam, you will just multiply with 2, because now it is for the interior long beam. Here the answer. Okay, just this is for exterior long beam, and to calculate for the interior long beam, you will just multiply with 2. Okay, because this equivalent UDL will be on now both sides, on this side and on this side for the interior beam. So just multiply with 2, so that is the equivalent width formula for the interior beam. Okay, so here the simplified form to calculate the load on load of wall on the beam. Okay, so for simplification, we do not take the whole load of the wall, we take just one strip, means 1 meter length. Just you have seen in the structure mechanics one or in the mechanics applied mechanics classes, we take for example 3 kilonewton per meter. Okay, means we calculate the load per meter, means for unit length. Okay, so here for unit length, 1 meter length, 1 meter length. Okay, what is the width of the wall and what is the height of the wall, we multiply with that. 1 meter length of the wall will multiply height of the wall and the thickness of the wall. Thickness of the wall mostly in millimeter, so divide by 1000. Okay, then multiply with the density of the wall, density of the brickwork, that is 1930 kg per meter cube, and then multiply with 9.81 to convert into Newton, then divide by 1000 to convert into kilonewton meter per meter. Okay, so after simplification, this value will come 0.019 multiplied by TW is the thickness of the wall multiply the height of the wall, and you will just get the directly UDL for the if any beam supported by the wall. It means any wall supported by the beams. Okay, now wall load on lintels. Okay, if there is sometimes the slab is too close to the lintel, so after the lintel with the little space the slab is present, and if the slab is present beyond that, for example slab is present above that, so if so much height is present, equivalent UDL on lintel, that is equivalent or the simplified form, equivalent UDL on lintel if the height of the slab above lintel is greater than 0.866 L. L is the length of the lintel, means if 0.866 times L portion of the wall is present above the lintel, okay, and slab is beyond, then the UDL will be calculated 0.11 into TW is the width of the wall thickness, okay, and L is the length of the lintel, okay, or the opening. So you will get the UDL for the for your lintel. Okay, you will design this lintel beam on this UDL loading. Okay, and if by chance your slab is downside, maybe if your slab is present here, you will not get this triangular portion. Okay, in that case, if the height of slab above lintel is less than 0.866 L, then the total wall load, okay, whatsoever the wall load will come on the lintel plus load from slab in case of load bearing wall. Okay, then the load from the slab will also come on this lintel. Okay, so how you will calculate the UDL? Then the equivalent width of slab supported, okay, multiply by slab per unit area. Okay, you will just take that width, okay, which is supported, equivalent width which is supported by slab. You will multiply with the slab load per area. Okay, so here for example it is supported by 1 meter or 1.5 meter. You will just multiply with the slab load area. For example, that is 3 kilonewton per meter. You will get the UDL. For example, if 1 meter length and 3 kilonewton per meter square is the slab load area, then you will get 3 kilonewton per meter UDL for the lintel design. Now this is the basic and simple calculations for the slab roof load and for the intermediate floor load. On the top of story of the building, okay, or at the roof, there slab present. For example, if that is 125, this is sample calculations. 125 millimeter, that may be 150 millimeter, 175 millimeter. And earth fill or the insulation material we use, or the soil we use, mostly 4-inch 100 millimeter, and the brick tiles that are 38 millimeter. How we calculate the total load of the slab? Okay, here the dead load, cell weight of RC slab, that is a 125 millimeter divided by 1000 to convert it to meter, multiply by slab density. Okay, reinforced concrete density, that is a 2400, and the answer will is 300 kg per meter square. Earth filling material, soil material, 100 millimeter divided by 1000 multiplied by with density of soil, that is 1800. The answer is 180 kg per meter square. Similarly, for brick tiles, the thickness 38 millimeter, we will multiply with its density 1930. The answer is 74 kg per meter square. So total dead load will be slab load, earth fill and brick tiles, that is 554 kg per meter square. That is the dead load. Now definitely there will be people movements, person move, their family member move on the roof, so there is another load, that is a live load. Okay, that depends upon the building type, residential building, commercial building, I have discussed in the first lecture. Okay, so live load for the roof, that is considered 200 kg per meter square. So now total factor load for the slab, for the slab, so that is 1.2 dead plus 1.6 live. That is the ultimate strength design. We apply the major factors on the loads and smaller factors on the material. On the material, I have shown in the previous example, like tension control 0.9, for compression control 0.65, multiple factors. Okay, these are the load factors. Dead load was 554 multiplied with 1.2, and live load, that is 200 multiplied with 1.6. The whole bracket is multiplied with 9.81 to convert kg into newton, then divided by 1000 to convert into kilonewton. So answer is 9.66 kilonewton per meter square. That the load calculations for top roof. Now the load calculation for intermediate floors or the center story floor. Intermediate floor, there was slab thickness 150 millimeter, screed or brick ballast plus 25% sand, the total thickness will be 75 millimeter. There is PCC, plain cement concrete 40 millimeter, and on PCC there will be tarazu in the common, that is called chips. Tarazu floor, that is 20 millimeter. Again same way, dead load, cell weight of the slab 150 divided by 1000 multiplied by density of slab, reinforced concrete, that is 360 kg per meter square. Brick ballast 75 millimeter thickness divided by 1000 multiplied with density of brick ballast 1800. Answer is 135 kg per meter square. And the total thickness of due to having same density 20 plus 40, that is 60 millimeter divided by 1000 multiply with density 2300. So the total dead load will be 633 kg per meter square. Now that is the dead load. Now here is the live load. Occupancy live load considered 250 kg per meter square. And the intermediate floors, there is in the offices most of the time there is a movable partitions. If movable partitions present, then consider this load. If not movable partitions are present, then consider not. Okay, let's consider in this example the movable partitions to make the rooms, small rooms for the office persons. So movable partition load, that is a 150. So the total live load, that is 250 plus 150, that is 400 kg per meter square. So total factor load will be again calculated same way. 1.2 dead plus 1.6 live. Dead was 633 and live here 400. So multiply with 9.81 divided by 1000 to convert into kilonewton. Okay, so that answer is 13.73 kilonewton per meter square. Now at the last, how to calculate the self weight of the beam. The self weight of the beam simply calculated width of the beam, height of the beam, and multiply unit length of the beams 1 meter. Okay, then multiply with the density of the concrete, reinforced density concrete, so that is 2400. You will get the self weight of the beam. Okay, this most of the time at the start analysis, we do not know what the finalized or the optimized concrete section will be used in the design. Okay, before we have to perform multiple trials, but performing for the trials we have to assume some self weight of the beam and then perform the calculations. For the assumption of the self weight of the beam, that here is the formula. Okay, B will be taken as L by 12 and H will be taken as L by 18. Okay, L is the span length, and then multiply with 1 meter, multiply by density of concrete, you will get 11.11 L square. Okay, that this is the dead load. Dead load factor is 1.2. You will multiply with 1.2, you will get 0.131 L square. Self weight of beam is required to be calculated at the stage of analysis when the beam sizes are not yet decided or finalized. So approximate self weight is computed using the above formula. Okay, so that's all for today's lecture. Have a nice day.